So, are we settled? Are you ready for this new episode of Control Systems? So welcome everybody to the second class. Last week, we did the first lesson where we introduced the very basics of control systems, and we mentioned how this is a very not so shiny subject, that it's not under the lights, but it's pretty much pervasive. It's a technology you find all over the place, and it's something that is very useful because it makes things work. Today, we're going to recap a little bit what we talked about last time. We're gonna wrap up the lecture because we didn't really finish it last time. And we're gonna take a step further and talk about modeling and in particular linearization. So basically, we're going to look a little bit more in detail about what do we plug in the boxes that we called the systems last time. So at the end of this class, if everything goes well, you should be able to derive equivalent system representations for different architectures, interconnections of systems, series, parallels, feedbacks, things like this. We will talk about the two main control architectures, feed forward and feedback, and we'll just point to what makes them characteristic and what are the ideas behind them. We'll thoroughly analyze them throughout the course. We're going to introduce a very particular and important concept, which is that of state or state variable. So up to now, we talked about inputs, we talked about outputs, but what happens in the middle? So there is this idea of state variable that is very strong, and we will talk about it today. Then we will introduce what hopefully will become your favorite equation of all time, your favorite math snippet, which is the linear time invariant system. We talked about them last time, and we didn't show what they are. And we will show through a few examples how we can derive linear time invariant systems for pretty much shiny nonlinear systems. So if you remember, we said last time that although we're studying a very sub class of systems, it's actually very powerful because these linear time invariant systems are very good representations of any arbitrary nonlinear system once we keep into account a few important ideas. That is, it's a local representation and it's a local approximation, and of course it introduces errors because it's an approximation by definition. We will then look at equilibrium points. What are they? Why are they relevant? And hopefully by today we should be able to linearize a few simple systems. So we talked about signals. We talked about systems. A signal is a map between two sets. We said let's imagine the numbers we plug into a signal to be something that comes from an idea of time, because we're going to study dynamical systems. Things change over time. We mentioned that, well, this time set from which we get the numbers could be continuous time, that's how nature works. Could be discrete, could be only the natural numbers, 0, 1, 2, but nothing in the middle. That's how computers work, and that's a relevant it's a relevant idea because all the control systems we will actually go and implement, at least most of the control systems that are implemented today are implemented in computers and microcontrollers. So we have to kind of, if you want to talk to a dog, you have to change yourself in a dog, right? So if you want to talk to a computer, you need to think like a computer in order to make things work. So we need to look into how things work in discrete time. So, and we introduced this idea of block representations. Control systems likes to see the world as a bunch of blocks with inputs coming in and outputs going out. So what is the box that processes the input signals into output signals? We called it a system. And a system, so is a map between signals. And we started describing systems. So, okay, there's many types of systems, but we can categorize them in, for example, static versus dynamic, or causal versus non-causal, or linear, non-linear, time invariant, time variant. These were very, very, very important things that allow us to study what a system is. So we looked at static systems or memoryless systems, and we said, well, a static system, what's the fundamental idea behind it? In a static system, the output at the current time is only a function of the input at the current time. There is definitely, there is no need to remember, to have a memory of the effect of all the past inputs on what is going on now, what is the output of the system at this current time instant. And of course, we don't need to worry about what is the effect of future inputs on the present time. We then introduced causal systems, which are, of course, the idea is similar to that of static systems, but this time we accept the influence of the past and the present input on the present output. Causal systems are systems where there is the principle of cause and effect. The effect follows the cause. So what really a non-causal system is a system where the future can affect the present. And that's something that we cannot find in real world systems, okay? It's impossible to realize, to physically build a system that is non-causal. We then introduced the linearity concept, and it's of course very important because we already know that linear time invariant systems is what we're going to study throughout this course. And the bottom line idea behind linearity is that of the superposition of effects. That is, if we feed into a system the sum of two inputs, then the output is the sum of the outputs that you would have if you fed into the system the two inputs individually. So there's this concept of additivity, and equivalently, there's this concept of if I send into a system a scaled input, well, then the output is just a scaled version of the output if I just sent in the regular input. This allows effects, that is the outputs of systems, we can just sum them up. If we know the system reacts to a signal, to an input in some way, and it reacts to another input, a different input in another way, well, if you put those two inputs together, just sum the outputs, you're done. Okay, very, very good thing about linearity. And then we finally analyze time invariance. A system is time invariant, but it doesn't really matter when you use it. It has the same output, regardless if the input is translated in time, if you were using the system yesterday or you'll use it tomorrow. So we saw that we could check for time invariance of a system if the output to receiving an input that is translated in time is just the same as taking the output of a system with an input at the present time and then just translating in time the output. So these four main categories, these four ideas to describe systems were useful to us to define the scope of the course. Now we said, okay, now in nature, this is all the stuff you will find. But really, what is it that we're looking at? We're looking at linear time and LTI systems, linear time invariant systems that are single input, single output. We introduced this block representation with one arrow coming in, one arrow going out. Well, yeah, of course, that arrow could represent a vector of many different signals. You could have multiple inputs. You could have multiple outputs in the general case. But these are ideas that you're gonna study later on in control systems too, for example. We're gonna focus on single inputs and single outputs. So why is this relevant? Well, it's relevant because, as we said before, although basically everything in the universe is nonlinear, all systems are nonlinear, most systems are nonlinear, linearity is a powerful tool to approximate the behavior of nonlinear systems locally. What does locally mean? It means around some operating condition. And today we're going to see what we mean by these operating conditions and what are the operating conditions around which it makes sense to linearize. And we'll call these equilibrium points. So last time we interrupted the class because now we talked a little bit about systems. We know what we're dealing with. But okay, we talked about one system. What happens if these systems are put together, like they're interconnected somehow? I would say that fundamentally, we can make arbitrarily complex connections that all boil down to three different types. Either you put two systems in series or in parallel, or you do this feedback link. So just to quickly recap, so what's the idea here? We want to derive what is an equivalent system representation if you have two systems in series. So basically, we're saying we want to look for something, sigma, that basically can represent these two blocks at the same time. So we want to look for something that is going to become mu equals a sigma y, where now the relationships between y and u are the same as if you had two different systems, a sigma 1 and sigma 2 in series. So how do we go about doing this? Well, just imagine the output of your first sig system, and you call it y1, and you've got something that goes the same. Output becomes the input of your next system u2. You have y2 here, that is the actual y. So what is y1? Well, y1 is equal to sigma 1 u, right? And this is equal to u2. What is y2? Well, y2 is sigma 2 applied to u2. And what is u2? u2 is sigma 1 times u. So we have the relationship we were looking for in the form of sigma 2, sigma 1 u. So basically this, we can just say when we have two systems in series, we can represent their composition by just ordering the systems in this way. And now we can just write one block sigma, as long as that sigma is the composition of systems in this way. Later on, we will see a little bit more in detail, yeah, but how do you do this composition between maps now? And it really depends on how you represent them. So it's something that we'll talk about later. Now, what happens if we have a parallel of two systems? Well, the principle is always the same. So here, just a notation. When we use these circles, these are represent sums, which could be additions or subtractions of signals. Typically, when nothing is written, we just mean a plus. So what's going on here? Well, here we have a signal that comes out of, again, the principle, the problem is always the same. Now we want to find what is something we can put in here to like a new system where that can have the equivalent map between the input and the output of this parallel connection. Now, so, well, how do we do this? Well, look at sigma 1, we received as an input u. Let's call the output of this y1 because it's the output of sigma 1. We can call this y2. What is y? Well, y is equal to sigma 1 y1 plus sigma 2 y2. And no, actually, this is not correct. The y is just equal to y1 plus y2, of course, and y1 is sigma 1 u plus sigma 2 u, because u is the input, the same input goes in both systems. So you can just sum up this together, you get something like this, which is the equivalent representation for a parallel, a parallel interconnection of systems. Are there any questions on how this is? This is really just to warm up a little bit, okay? Are there any questions regarding this? Nope. So now we'll make it a little bit more fun, and we talk about these feedback loops. Now, in particular, here it's a negative feedback because we are subtracting the feedback branch, which is this one underneath, okay? So what's the idea here? Well, let's say always this is the signal that goes into, so the idea is always the same. We want to find an equivalent block that represents this interconnection. That's called the input to sigma 1 u1. And so what is y? Y is going to be sigma 1 u1. But what is u1? Well, u1 is u minus, this time, whatever comes out from here. So it's u minus, what is it that comes out from here? Well, we're taking y and we're feeding it back. That's why it's called a feedback. That means we're taking whatever is the output of the first signal and we're making it become the input of the second signal, of the second system. So it's u1 is going to be this u minus this output y2. And y2 is nothing but what? It's nothing but sigma 2 times y, which this time is the input to the second system, right? So if we go and take this and put it in here, what we get is a sigma 1 times u minus a sigma 2y. And this is sigma 1u minus a sigma 1 sigma 2y. Okay, so what are we going to do with this? Let me just rewrite it down here. We've got, let's just copy it out. So let's do every single passage now just to be clear. Now you see that there's y on both sides of the equation. I can take this part and just slam it on the other side. So we get y plus sigma 1 sigma 2y is equal to sigma 1u. And now, again, what's the objective? Now the objective is finding a relationship between the input to the whole interconnection, that is u, and y. So we're close now because we have the y's here, we have the u there, but we need a simpler relationship. So, well, here we can just bring y outside, and this, let's for now write it like this. And then if you have, we'll look into it later to see what it means. So we just gather the y. I wrote an I here instead of a 1. And what I mean by I in this sense is I can, since sigma 1 and sigma 2 are not really numbers, right? We can imagine them as it was like a coefficient, a 3 or 2, or just a scalar that multiplies. But it's more correct to imagine them as function, as maps. So as the I is put in place, is a generalization of a 1. It's an identity map. It's a function that doesn't change anything. It's like the identity matrix. If you multiply an identity matrix to another matrix, you don't change. It's the neutral element, right? So just to keep it general, again, the objective is identifying this y, so we can pre-multiply this, multiply on the left by basically the inverse of whatever is there. And I need to do the same thing here. And what we get is that these cancel out, and we have y is equal to I plus sigma 1 sigma 2 inverse sigma 1u. And this is the feedback connection that we call sigma, okay, that is up here. So this is very, very, very important. Note that a negative feedback connection, that is, you are subtracting the feedback branch to the main branch, turns out to have a plus here, so don't get confused. Of course, if we were to change that sign into a positive feedback connection, it would change otherwise. So why are these things relevant? Now we're just playing around with the math a little bit to see that it is possible to represent different interconnections with summarized systems. But again, now, so this whole course is called control systems now, so really we want to control stuff. And what does it mean to control? What are the objectives of a control system? A control system is worried about three big things. This is really, it applies everywhere in control systems, regardless how many courses in control systems you're going to do, if it's going to be nonlinear, adaptive, iterative, whatever complexity you want. At the end of the day, it's all methods to achieve these three objectives we're going to talk about today. First one is stabilization, okay? So we haven't introduced the concept of stability yet. We'll get to that later on. But the idea of stability is if we send an input to a system that is not catastrophic, well, the output will have to be non-catastrophic. What does it mean? Stability means the system does not blow up, does not break. If I send finite energy as an input, the output is going to be a finite energy. If I were to touch this and this thing were to fly to Mars, then probably the system would break down, okay? So of course we will define this mathematically later, but the fundamental idea of stability, which is the first objective of a control system, you want to get this nailed down first, is that you want to make sure things don't break down, don't blow up, okay? The second big objective, which is, it sort of puts these things together, something we could call performance. So basically, okay, now we ensured through stability that things don't break, but that things don't break doesn't mean they're working well, right? They're not, and what does it mean to work well? Work well means they work according to specifications that are defined by the user, by the engineer that is actually designing this control system. So we can, at this point, just break down performance as two properties, regulation and tracking. That is, well, if the designer wants the system to behave in a certain way, what does it mean? Well, it means that we would like the output of the system, the final output, to be very close, possibly, ideally identical, to what we define the output to be. We say we want the output at every single point in time to be this function, arbitrary, that we just write down because we know that that's what we want the system to do. So the whole objective to have a performant control system is to make the output be as close as possible as that reference signal. So when this reference signal is just a constant, for example, take a door like this, no? It's a system. We want to, what's the control objective? The control objective is that when somebody pushes it, it goes back to being closed. So how did the control engineers fix that door? Well, they just put a spring on top. So if you just push it away from the equilibrium point, it just gets pushed back, right? So there, the set point, that is the reference signal, is a constant. It's the constant position 0, which is closed, okay? So a system, the problem of regulation is, are we able to maintain a constant set point regardless of disturbances? Suppose there is a strong wind here, random wind going in and out of the room, well, that would be a disturbance for the door. Is that system, is the regulation problem solved well there? Well, yeah, it depends on the how do you call it, the spring you put up on the top. It might work better or worse. And similar is the tracking problem, that is to follow a time-varying reference signal in spite of everything that might affect the system, that is part of the system dynamics or not, or some effect of the environment on it. Finally, there is the problem of robustness, which is the third big objective. So stability first, performance the second, and then robustness. What is robustness? Robustness means that, say we designed a controller for a system that we assumed to be modeled in a certain way. We assumed the system followed some behavior. And we designed our controller to be stable and to be performant according to whatever specifications that we define. A controller is said to be robust when that same controller that was designed for the nominal system works, even if the system is slightly different from what we thought it was. I don't know if you remember last time we mentioned, but we'll say it again today. The models are mathematical representations for a physical phenomena, for something that's going on. They're not the truth. It's not like things actually go, things are the math. Everything goes as if the math representation was right. So the bottom line is that all models in the world you'll ever come up with are wrong. The point is, they're wrong because you're always neglecting something that you consider negligible, non-relevant for the specific task for which the model is produced. So there's always going to be some imperfection between the mathematical equations that we use and the actual behavior of the physical system. So this is tricky, right? Because if we design our controller assuming the system would behave according to some mathematical equations, but then in reality, it really is not that, or at least it's close to that in some sense, but it's not exactly that, those mathematical equations, will the controller still work? So a robust controller works. So robustness is an advanced topic. It kind of is the whole point of control systems too, and we'll touch upon it later in this course, but we're not going to do this systematic. So, okay, how many of you have downloaded the slides and have them in front of you? Please don't look at the next ones, otherwise they'll spoil the fun. So, okay, so now we understood what we want from a control system. How do we go about doing it, right? So we understood what a system is, pretty much. At least there are many systems. We care about some subset of them very well. We want the output of the system to behave in some way. How do we start? Where do we start? Well, let's take an example. Let's take a brick wall, okay? And let's suppose that we want a brick wall to fly because that's our design objective. So this is just about like trying to take out the fundamental ideas. So we said control systems is about making systems do what the user wants them to do instead of what they would naturally want to do. So what would naturally a brick wall want to do? A brick wall probably will want to stay on the floor, right? It's not going to fly spontaneously. So how are we going to make a brick wall fly? Ideas are welcome. Please do not look at the next slides, otherwise it's not fun anymore. So come on, we can stay here forever until somebody says, there are many approaches to this. How do you make a brick wall fly? How would you start? Do I need to call out people? You want to give it a shot? I'm talking to you. How would you make a brick wall fly? Oh, may I throw this to you? Careful. Okay.
You could fix it to a drone or to a flying object.
That is a sensible way forward. Yes, but then it's complicated, right? Because depending on which brick wall you have, what kind of bricks you use, you need a bigger drone, a smaller drone, or a bigger airplane. Yes, that's a good way forward, but what would be the ideal way of doing it? Suppose we had a perfect controller. We're trying to find what is the best possible approach to do control systems, to structure our work forward. So what if, other ideas? Anybody can guess how would you make a brick wall fly? Yes, could you just throw that thing until it gets there? Maybe an intermediate step would be, great.
You could push it, for example, over an edge and let it drop.
Oh, well, yes. I guess that's a matter of performance, right? It's all in the specifications. So, yeah, sure, if you fall from a cliff, you still get wind in your face. You still, feel like you're flying, but you're technically falling. I guess what's the difference there? I don't know. I mean, if you put something in orbit, you could say it's flying, but actually it's falling all the time. So it's a fuzzy border there. But yes, that's a creative approach. Well, again, it would be kind of, yeah, sure, but you need to go there. You need to take maybe a truck or whatever to push the brick wall, and it wouldn't be flying for a long time, depending where you are. So what instead if we just divided it by a brick wall, the same brick wall, and then we multiplied it by an airplane? So the brick walls would cancel out, you would have an airplane, and you get the airplane to fly, right? Beautiful. This would be perfect if we could do it. And that is the first and most fundamental approach in control systems. It's the idea of feed-forward control. The essence of feed-forward control is so-called plant inversion. What does it mean? You have a system you want to control, which is a brick wall you want it to fly. You need to have a model of your brick wall. I didn't say just any brick wall in the world. I said this brick wall. It's red, it's that size, that shape. If, through plant inversion, what you do is you cancel out the system you want to control. And then you replace it with whatever you want. But the fundamental idea is just divide a brick wall by an identical brick wall and multiply it by an airplane. So how do we write this down now in a little bit more of a structured way? We looked at serious connections, and now let's take a step forward, away from the domain of mathematics and a little bit more in what the terminology we're going to be using going forward. We call the system we want to control no longer sigma, but P, okay? Where P stands for process or plant, okay? The most common way of calling the system one wants to control is the plant. So this is the plant, and it's the objective of our efforts. We want to make sure the output of the plant, Y, this is the output of the plant, behaves in a way that is very close to how we want it to behave. That the way we want it to behave is defined in this signal here, which we call a reference signal, sometimes referred to as a set point. So we talked about at the very first class, we said, well, the control problem in general is figuring out what is an input signal in time such that the output then does whatever we want it to do, that the output follows the reference, right? So the whole deal here is, the whole problem of controls is how do I figure out U such that, U in time of course, such that Y is as close as possible to R. Well, the first approach, which follows the idea of feed-forward, follows the idea of plant inversion, follows the idea of making a brick wall fly by dividing it by a brick wall and multiplying by an airplane, is just to add some other system in front. We call it F because of forward, feed-forward. And let's look at what happens. So you remember from the serial interconnections that we saw like literally 2 slides ago that the relationship between the output and the input, which this time is the reference signal, now don't get confused with the U's that we used before. Here it would be PFR, correct? Anybody disagrees with this? I will do mistakes all the time. I actually did a mistake or 2 in the last lecture as well, some of you noted. So please always double check my math and let me know if I'm doing things wrong. So this is correct, right? Where is the division between the brick walls here? F is a design parameter. It's the controller. It's what we want, what we're designing in order to achieve the objective of making y equal to r. Well, what if we chose F to be equal to the inverse of P? We're dividing P by P. So this would then become P inverse R. These cancel out. Y equals R. Boom, we're done. Finish. Let's go home. Control systems doesn't need to exist because we solved the problem, right? By simply multiplying the input to a system by something that is the inverse of the process you want to control of the plant, we can get instantaneous following between the output and the reference. That's what the math says, and the math is correct, okay? So what's the deal? Why are we here, and what are we going to do for the next 11 classes or whatever, right? So what's the basic idea here is that if we have a model of the plant that is correct, that is, the P there is actually the P of the process, it describes mathematically exactly what's going on, then we can just invert this process and put a feed-forward block, and at that point we can basically achieve whatever we want. We can even make a brick wall fly. What's the problem? The problem is that every model is wrong, so you'll never get the P right. Even the simplest of systems, our math is always captures the essence, captures what is relevant for us to achieve the task that we set forward. But is it really what's going on? Plus, minus, maybe yes. Sometimes it depends, right? But there's always going to be something that we'll call modeling errors. So this inversion really doesn't work out. Because division, something divided by something, works and gives 1, if and only if the two things are identical. If they're not, then, well, bets are off and this doesn't hold anymore, okay? So just to get the idea here, feed-forward is one of the two main architectures of control systems, and it is ideal if we have a perfect knowledge of the process, the plant we want to control. It works by simply processing the input that goes into the plant we want to control with some prior knowledge. That is this prior block F. As you see, as it might be intuitive, we're just, through this control approach, we're just choosing more or less wisely what we're feeding in the system. But we're not really changing the system itself. We're not altering its dynamics. We're not engineering the way it dynamically responds to inputs. We're just trying to choose the right inputs such that the output is what we want it to be. So this is something we will look into more detail as we go forward, but it's a fundamental difference between feed-forward and feedback. Feedback, instead, as we saw before, has this idea of we grab the output of the system and we compare it by doing a difference to what we would like the output to be, the reference signal. So if the reference signal and the output of the system are identical, then the error is going to be 0. This E here is often referred to as the tracking error. And therefore, the controller won't do anything. The input is going to be whatever it was before, and everything is fine. If instead the output of the system is different from what we define as an error, as a reference, then there's going to be an error that is different from 0. The bigger the difference, the bigger the error. If we take this signal that now encodes much more than just what we want the system to do, but it tells us how bad the system or good the system is doing with respect to what we want it to do. It's an error signal. It has much more information inside it. If we feed that signal to a block that we're going to have to design somehow that we call a controller, which is the C part here, Then we will obtain an input that will allow our system output to behave accordingly. So what's the idea? The idea is that, I mean, we can't really generalize too much at this point because there's basically decades of literature on how to do that C there. But the fundamental idea is that, well, the bigger the C, the bigger effort we're going to put to fix the error, okay? So if we have a big C, means even if the error is very tiny, we're gonna push a lot. We're gonna change the input a lot so that the system compensates. One of the issues of feedback is magic in the sense it works really, but there are subtleties because feedback now changes the dynamics of the whole plant because you're feeding, because we are sending into the system something that is no longer just an arbitrary signal designed by us to achieve an objective, but it's something that is defined by the output of the system itself. So it is possible by choosing, by engineering C in some specific way, to actually change the dynamics of the system of the plant, to make this whole equivalent block behave in very interesting ways. But if we write it like this, we're only telling part of the story. This is a very ideal situation. What happens in reality is that, before we get there, what happens in reality is that we have a plant we want to control, we have an input and we have an output, correct? So what is an output of a system? An output of a system is what could be potentially anything, but really in practice, it's something that we want to feed back, right? So if we want to feed back, it's something we must know. We must be able to measure. Measure is the key word, okay? So if you can't measure it, you don't know it. If you don't know it, how can you feed it back to a controller? A controller is something designed by us. You can imagine a controller as a computer program, okay? It gets a reference, which is designed by us. It gets this output, which somehow we need to know what it is, otherwise we can't feed it to the computer program to do whatever calculation it needs to do. So we need to measure it. The outputs are typically, in reality, referred to as measured outputs. And really, what's the difference between a measured output and the true, real output of the system that only nature knows? The difference is that we have to put an instrument to measure. It's called the sensor. So really, a more accurate representation of this part would be we have our input U that goes into the plant, which sends out an output signal, which we don't know anything about until we plug in a sensor. So a sensor might or might not have an independent dynamics. Imagine a camera. You're using a camera to measure what's going on. Well, there's lots of stuff going on in a camera. There's circuits, there's light coming in, out, time. So the sensor itself might be another system that influences the whole game here. And you finally get a measured output. This measured output is the only thing we actually know that you can effectively feed back and then do everything you want to do with it. So what we're going to do for all this course is not get into the details of what sensors we're going to use, okay? Because we could make a course only on that. We could make a course only on one or two sensors. But we're going to acknowledge that there is this extra step. And how do we acknowledge it? By saying, look, whatever you use to measure, you're introducing an error. You're introducing something, some mistake, some other signal. And we'll call the signal noise. So really, what we will see going forward is always the output here that is summed up with some other signal that we might call noise to produce a measured output that is then fed back. To the system, okay? And that already is something closer to reality because we can then say, okay, what sensor are you using? Well, depending on the sensor you're using, we can change the properties of the noise signal. Typically, noisy signals are something that are, you can imagine it as white noise. High frequency noise, pretty much all over the place, that jams things up a little bit, messes your measurement a little bit. Of course, it might not be white noise, it might have some very special properties. So do you know what white noise is? I assume that, no. Okay, so we will be able to give a technical definition of white noise once we introduce Laplace transformations in the frequency domain. But the idea of white noise is that it's a very fast varying signal that can have, that is, let's say, equally effective regardless of the signal that is being measured. Let's put it like this. So regardless of what we're measuring, we're adding some component that is a random number between, imagine it, between +1 and -1, or whatever it is, between +a and -a, okay? And between two successive time steps, well, this error could be any number between ±1a. So there could be very, very quick variations between two successive time steps, and that we're going to see later is going to be a big issue. Okay, so we got this idea that we can't really deal with an output without measuring it. This introduces a problem. We'll call that problem a noisy signal. But then what about the input part, right? So what's the equivalent there? So we want to send an input to a system. Okay, in principle that works. How do you do it in practice? So we realized that a controller, what is it in practice? In practice, you can think about it as a computer program. Of course, it can even be done in analog ways, just put all springs together, stuff depends on the system you want to control. But let's imagine it as a computer program. It's a logic, it's a decision-making process, okay? Based on what you want to do and where you are, you'll take some choice. That's the controller, it's a decision-making process. But then whatever the choice is made, that choice has to be implemented in the real world. It has to become an input to the system. The system is a physical thing that you need to prod. Okay, if this is the system, I need to touch it to move it. It's not like I made the decision and it's going to move in itself. So really what goes on here in the middle is that whatever is the output to the controller is some decision. Let's call the decision V, okay, because it's close to you. But I'll need something, some physical apparatus, a transducer, something that we call an actuator, to actually translate that decision into something that can physically affect the system. And that actuator could be a switch, could be a valve, could be a current of some kind, a circuit. Whatever it is, it might or might not introduce some dynamic in the system, an additional block that is called the actuator. Now, and the actuator has the job of transforming a decision into an actual physical signal appropriate for the system we want to control that's going to move it in the way we want it to move. Of course, it's difficult to be precise here because a system could be many different things physically, right? And here it produces a U that then goes into the P. Similarly to what we've done with sensors, we are not going to go into actuators. You can do full courses only on that. What we're going to do is acknowledge the presence of an actuator, and we're going to say, look, there's nothing, I mean, we won't look at any dynamic block here, but we're going to say there's going to be a signal that messes things up a little bit, that actually changes the output of the controller into the input of the system. And we'll call this signal coming here a disturbance. Typically, disturbances are different from noises because they vary more slowly. Let's leave it at this for now, but we'll see later on. We need the tools of the frequency domain to characterize the signal, and we'll introduce them only later. So, to wrap it up in the next minute, feedback is fantastic, but it has one problem. It takes the noise that comes at the output and brings it back into the loop. It injects noise in the system, and that might have catastrophic repercussions. So a feedback loop can actually make a stable system unstable. Might make something that was working perfectly fine blow up just because you're sending back the output of the signal to the input. So it's a very powerful tool, but Every time there is power, it has to be used responsibly, so we have to be sure that we design the controller in a wise way. We can continue in 15 minutes. Okay, so I realized that I did something wrong and nobody told me. Why? Why don't you? So the bell rang again, right? We should start. Yes or no? Yes, no, maybe? Yes, thank you. So I thought it was the pause from 11 to 11:15. It's not. It's from 5:02 to 10, right? 5 to 11 to 10 after 11. Huh? It's only 10 minutes? Good to know. Okay. You just get mad at him. You just lost 5 minutes break for the rest of the course. Okay. Let me close the door here. So we talked about feed forward. We talked about feedback. Now, what happens, of course, both have strong points, strengths, have weaknesses. We can definitely put them together and we get what we call a 2-degree of freedom control architecture. This is basically the most general control architecture that we will be treating for a while in this course and probably even in a few other courses and controls if you're going to take them. And what's the bottom line idea of this 2-degree of freedom architecture? Well, if you knew everything perfectly about the plant, the feed-forward would solve our problems. But really you don't, so you make the best guess you can, and you send that as a feed-forward signal, and then whatever is left, whatever the errors are gonna, that are gonna be residuals of this difference between your insight and the actual world, we feed that back, and we do a feedback controller to compensate for those things. So it really combines the advantages of both feed-forward and feedback architecture. Now we're going to start doing something that is really important. Like now we talked about the general things. I hope you gained a little bit an intuition about what we're trying to do and how we are going to go about doing it. But control systems is sometimes referred to as the most mathematical of the engineering, let's say, disciplines. If you check like a control systems paper, let's say, who loves the control systems will say it's the most mathematical of the disciplines. Who doesn't like control systems will say they're all failed mathematicians. All people that wanted to be mathematicians but were not good enough, they became control systems people. But anyways, the bottom line is that you'll see a lot of math in control systems. If you read a control systems paper, you'll see it has like the approach, like theorem, proof, lemma, you know, like and that's because it uses some theoretical, let's say, ideas that are very powerful and very useful. And I think one of the most possibly counterintuitive, but relevant is that of state space variable. And once we define the state space variable, we can define state space representations, which are going to be basically what we're going to do for the rest of the course. State space representations are a way for us to actually write the system. So we talked about systems, but now, okay, how do I write the mathematical relationship between input and output exactly, okay? You do it through some sort of equations, of course, but, well, we can write equations in many different ways. State space representations are a way to standardize the way we write relationships between inputs and outputs. And thanks to this standardization, then we can make general rules that's gonna cover a bunch of infinite different cases, okay? So but let's get to that. So in order to make this possible, we need to introduce the idea of state variable. What's a state variable? So let's step back a second and rethink about causality. What's causality? The idea that the future cannot affect the present, and we're good with that, okay? So in a causal system, the present output is affected by the past and the present. But the past is the big deal, right? Because the past is everything from minus infinity in time to now, to t. It's a lot of stuff. Minus infinity to now is a lot of stuff. It's a lot of, imagine that in order to take a decision, in order to say where I'm going to be now and now and now, every time instant, every time to make that decision, you have to remember everything that went on since you were born, okay, from the beginning of time. it's not really convenient. So what can we do to fix this? What we can do is that we can introduce something, a variable, that summarizes all the effect of what happened from the beginning of time up to some arbitrary time instant that's closer to the present. For example, let's call the present t1. Let's say we choose a t0, which could be an hour ago, it could be a minute ago, it could be a second ago. We introduce this concept of state variable as some mean, some way to summarize all the history from the beginning of times up to time t0, such that all I need to know to determine the output of a causal system at the present time instant is that state variable at time t0 plus the knowledge of the input from t0 to t1. That's much more manageable, right? Because I don't need to remember everything that happened to me, all the stimuli I received since I was born. But I just need to remember what is the input that affected the system from t0 to t1, which could be in the last day, in the last hour, in the last second, in the last millisecond, or whatever it is, right? Does this make any sense? Of course, I haven't said anything specific. I didn't tell you how to define a state, but the fundamental idea of a state variable is a mathematical something that summarizes the effect of the input on the system from the beginning of times to some point in time before the present. So we'll see examples today, of course. Generally speaking, a state variable can be one number, could be two numbers, could be three, and many numbers. The general way of thinking about it is a vector of n variables. Each component of this vector, each one of the state variables, is a signal that changes in time and can have real values. So, just to write this, to show this in drawings, what we're saying is, so for a causal system, this is the output, right? The output that varies in time somehow. I want to know how I'm going to determine the output at the present time instant. Well, without state variables, what you need is everything from the beginning of time, from minus infinity to here. You need the knowledge of the input from ever in order to determine what the output at the current time instant is. Well, definitely don't need the future, which is good, right? And this, we can throw it away. But still, this is a lot of information. It's actually infinite pieces of information. So we introduced the concept of state variables so that all we need to do now is just know the value of the state variable at some time 0 that comes before t1, and then we'll have to know what the input is in that restricted amount of time, okay? And that will also allow us to determine what the output at the present time instant is. So what are good state variables? So what's the idea behind a state variable? Like now, forget about the infinite different ways in which it's gonna decline itself depending on the plants that we're gonna study. But what's the idea? The idea is it keeps track of what happened before. It's a memory, okay? It's the memory of a system, basically. So every time you wanna physically, because it's kind of the job of a control engineer to model a system, now to find the mathematical relationship in such a way that it's convenient to use. So you kind of get to choose with some degree, you get to choose what the state variables are. Because actually it turns out that there's infinite representations of state variables. There's not one right way and anything else is wrong. There are infinite different ways in which one can describe state variables. Some are more convenient than others. We'll talk about it later. But let's take an example. So we've got a water tank. We're filling it with water or whatever you want. What's the input? The input is the amount of water we send in the tank minus the amount of water we send out of the tank, okay? So the net flow amount of water that goes into the tank for some time instant. So suppose the output is how much water is there in the tank, the height of, suppose we know the geometry of the tank, so we just want to know the height. Well, to determine how much water there is in the tank, you need to know the input from the beginning of time till now. You need to know since the tank was built, how much water at every time instant went in, how much water at every time instant went out, in order to determine what's the how much water is there left in the tank. That's one way of doing it. If instead we were able to measure the height of the tank, well, we could say that keeps a memory of what's going on. I don't really need to remember all the history. I just measure how much water, what's the water level, or I weigh how much the tank is heavy, and I've got an idea now of a number, a variable, that summarizes the effect of the past history into the present output. Does it make any sense? It might be slightly confusing here because this is a case where the output is equal to the state variable. So there's a superposition of that then. But the idea is you can choose a physical variable that keeps in track of the past effect of inputs on the system. It stores the memory. Sometimes they will tell you to choose a state variable. The state variables are like energy reservoirs of the system, whatever that means. So that if you study how the energy reservoirs change, then you can tell the dynamics of the system. Maybe that's another way of saying it. So there are many ways to choose what the state of a system is. For example, before we could have said the height, we could have said, no, it's two variables. One is a third of the height, and the other is 2/3 of the height. Or we could say, no, we weight it. So that's basically the height times a couple of constants. So there's infinite ways to determine state variables for a system. But some of them are better than others. In particular, we talk about minimal representations. So what is the smallest possible, I told you, no, it's a variable, imagine it as a vector of n components. What's the smallest n such that we can effectively tell what is the output at the current time instant with the knowledge of the input only from time t0. And this is so important that we actually define the dimension of a system as how many state variables it has. How many state variables do we need in a minimal representation to describe what the output will be, knowing the input? We are assuming, kind of, up to now, that we're talking about finite dimensional systems. Okay, so this n is n, it's a number, it's less than infinity. But you can very well do all of this with systems that have infinite states. And there are some very practical physical examples of systems with infinite states. We'll look at a few later. But we are not going to be treating infinite dimensional systems in this course. So it can be shown that a linear time invariant system with in this case, let's talk about single input, single output, but this formulation holds for MIMO. Let's just say multi-input, multi-output. It has this representation. Okay, this becomes basically this should become your favorite equation. Like I should be able to wake you up in the middle of the night. You don't need to remember your name, but you need to remember x dot equals ax plus bu and y equals cx plus du. Okay, it's like super powerful representation. So what is this stuff? This is, we call y, we already saw y. This is the output of the system. We saw u already a bunch of times. This is the input to the system. We call x the state variable. Okay? And so MIMO system, multi-input, multi-output, means u is a signal that might have, I don't know, p components. Okay? So this means u is a vector that has u1, u2, u3, up to up components. Each one of them changes in time. Okay? This would be a p-dimensional real vector, and I use this notation to represent it. The output could be, in a MIMO system, something more than one output, so we could say it's like an L by 1, whatever, where L is a number, okay? But this doesn't really matter to us, because in this course, we're just going to study single input, single output systems, where u is a variable, it's a 1 by 1, so to speak, and y is a 1 by 1, okay? In the continuous representation, continuous time representation But so if you have one input and one output, does it mean that the state is one, has dimension one as well? Well, no. And why? Well, so let's look at this. We actually said that X can have, in general, n components, where n is the dimension of the system. So if U is a 1 by 1, and X is an n by 1, which is a vector of n components, and here on the left side of the equation we have d in dt of x, which is x dot, which is the derivative in time of x. It's always an n by 1 vector. Well, what are A, B, C, and D now? A, B, C, and D are matrices that define the relationships between the inputs and the outputs. And what are the dimensions of these matrices? Well, here we can use some tricks of linear algebra. We know that so the left and the right side of an equation have to be equal, right? Because it's kind of the whole point of an equation. This means that if you have an m by 1 vector on the left side, you'll have to have an m by 1 vector on the right side, hand side, otherwise they'll never be equal. So if this is an m by 1, then A has to be a matrix with dimensions n by n. Does anybody disagree with this? There's kind of a trick to understand what's the out. So if you multiply, let's say a random matrix, let's call it M times a vector, let's call it B. Suppose the vector has arbitrary dimensions, small m by 1, and the big M matrix. So you know that matrix multiplication is a row by column operation, right? So it means that the second digit, the second dimension of the M matrix must be the same as the first one of the vector, otherwise there's no way this is gonna work. So if you just know, sorry, let's say I put an n here, then the output, it's like if these two dimensions cancel out and the output is n by 1. Okay, so if you put here, A is gonna be n by 1. So I'm using this trick here to say, okay, if x is an n by 1, then the middle component of A must be the same as the vector, then the left-hand side must be whatever comes on the left-hand side of the equation, otherwise they're never going to be equal. So A is an n by n matrix. And the B is going to be, now that we got this, an n by 1, because U is a scalar, is a 1 by 1. And if we use the same arguments underneath, we see that U is a 1 by 1. We said that Y, because we're studying single input, single output system, is a scalar, is a 1 by 1. So D in this case must be a 1 by 1 as well. And X is an n by 1, so C must be a 1 by n. Notice A is, so we can represent this equation graphically, if you want, as a vector that has n components is equal to something that multiplies another vector x, this would be x dot, this would be x, times a square matrix that is an n by n, this is an n by 1, plus we have an n by 1 times plus 1. This, can you see what's going on? These are just the dimensions of the matrices that we just represented. Well, with the C, we have an 1 by n, so it's a row column times, an n by 1. So you do row times column and you get a 1 number, which is the Y. And D times U is just a 1 by 1. Okay, so we mentioned that the state represents some sort of measure of the memory of the system. Turns out, if the state has dimension 0, means you don't need to keep memory of the system. And guess what? The system turns out to be static or memoryless, as we defined it before. And, well, yeah, these are, once you go and check back the definitions, it's straightforward. As we said, a system is strictly causal if only the past affects the present, but not the present itself. Note that the past of the input affects the present of the output. It's not about the state, right? So all you need to know to check for causality is this: y of t, the output at the present time instant, is a function of x of t plus d of u of t. So if d were equal to 0, which happens to be the case for most real systems, then the system is strictly causal because the input at the present time does not affect the output at the present time. So, okay, now let's see a few of these things in practice, okay? So again, I will repeat this hopefully a million times throughout this course because it's really important. All models are wrong, but some are useful, right? This is a famous citation. But so always keep in mind that what we're doing is a way to describe what's going on. Everything goes as if our equations were describing reality, but really this is an expedient for us to get something to play around with so that we can take decisions, okay? It's not really what's going on. This is the same example as before. What's the input to the system? We've got something coming in, something coming out, okay? So the flow of water is the difference. We know that the height here is the water level and kind of keeps track of how much water there is, so the past, the history of the inputs. And suppose we know the geometrical properties of this tank. We know it's a circular, cylindrical, with some cross-section area, or whatever it is, okay? So what's the dynamical model? What does it mean, the dynamic? What's the model of the system? What's the relationship between the input and the output? Well, the height of the tank is gonna vary depending on how much net flow comes in, right? So if the net flow is positive, if there's more water coming in than water going out, then this level is gonna go up, and vice versa. If the output is the U minus is bigger than the U plus. And of course, how much it's gonna go up and down depends how big the tank is, right? If you're filling up a straw, you need very little water to get the water level up a lot. If you're filling up a big thing, so it's 1 divided by this cross-section of the tank. Okay, so how do we choose this model? How do we get to a state space representation, to an x dot equals ax plus bu? Remember that what we're heading to at the beginning, so this is kind of something that I must have written up 3 million times in my life, so I might forget to add the proper notation. So keep in mind that every time that I'm gonna write x dot or u of y, it's always intended to be x dot of t, y of t, u of t, unless it's specified that it's a constant variable, right? So, but let's write it out correctly. X dot of t is ax of t plus b u of t, and y of t is cx of t plus du of t. Okay, so this is the model of the system. We choose the output y to be the same as the state variable and to be this h. So how do we rewrite this? Well, dh in dt means x dot is equal to 1 over tcs times u. Okay, and the output y, we chose it to be, what we measure is actually the height of the tank. So y is equal to x. So how do we get a, b, c, d out of this? Well, A is the matrix, the state transition matrix is what relates x dot to x. There is no x here, right? Where is x? So A is equal to 0. This is like plus 0 times x, right? So A is 0. What's B? Well, B in this case is 1 over TCS. It's what relates the input to the state variable dynamics. Then C and D, well, C in this case is very easy. It's equal to 1 because it's how the state is related to the output. And the D is, in this case, is 0 because the input does not directly affect the output. And sometimes you'll find it written like this, where you just put together everything in a big matrix, but it's just a notation, okay? It's just a way to synthetically put things together. Okay, so that was relatively easy. Why is it relatively easy? Because this is an integrator, right? We call it an integrator. Why? Well, because at the end of the day, now we use all this fancy representation that is coolant control system, so let's not lose sight of what is it that we're actually doing. So suppose that you knew nothing about control systems and you wanted to solve this equation, you wanted to find what's going on, right? Well, y is equal to x, and this means that y dot is equal to 1 over TCS times u. U is given, I know the input. What is the output? Well, this is a derivative. The inverse operation of the derivative is an integral. It means this is just 1 over ts u of t in dt between some time instance, right? We put a tau here to make it right. So it's an integrator because the input and the output in this case are related by an integration operation, okay? Let's make it a little bit more complicated. It's a first order system. So what does this mean? This is, we're talking about the dimension of the system, okay? So it's a first order system, and we'll see why. So well, what's the problem here? Well, we have an environment, we have a heater, we somehow get this radiator to produce some heat. The heat is gonna raise the temperature inside the room, okay? The room is going to have an external environment. The external environment is at a different temperature. It's at the external temperature, T. So what's the model of the system? There's going to be, depending on the input is going to bring heat to the system, but the system is going to reduce its temperature depending on the difference between, we're talking only about conduction through the walls here, so let's suppose C is the thermal conductivity of the walls. It's a very simplified problem, but here the point is just to show that there is the difference between the T and the T actually affects how the dynamics of the inside room temperature goes. So, well, we are looking for something that we can define as a state variable, right? Something that can keep track of the history of everything that's going on, all the T's outside, all the radiator power that we gave. Well, that could be measured just by measuring the temperature in the room, or the difference between the temperature in the room and the temperature outside. So we assume in this specific example that y is equal to x and it's equal to t minus t, and let's see what's going on. So here we have d in dt is really, so here we are, of course, assuming that the temperature inside the room changes, u of t changes, but the environment has infinite thermal capacity, so the external environment temperature stays constant, okay? So this we can say is a constant. And what's going on? Well, the derivative in time of t minus dE is very much the same of the derivative in time d in dt, right? Because the derivative of a constant is 0. So we can call this thing here dx, dx in dt, which is a long way to say x dot. Mx dot equals to c times this that we defined x as x plus u, okay? So we have this system, let's rewrite it in a proper way, and it's x dot, we want to always remember this is where we're heading to, right? We want to put the system in this form. So we want to get rid of this m basically, so we divide by m left and right side of the equation, so we get the c over mx plus 1 over mu, and y we said it's equal to x. So again, who's gonna be who? Well, this is gonna be A, this is gonna be B, this is gonna be C, and this is gonna be D, right? Same structure as before. Why is it a first order system now and not a 0th order system as before? Well, because A is different from 0. So we need the state variable x appears explicitly in this dynamic equation, and it's a vector of dimension 1. It's one variable. So, and it's t minus d. And we'll see this by looking at the dimension of A. A is a 1 by 1. Where this is n. If you remember, A had dimensions n by n, which n is the dimension of the system. So just look at how big A is, and that tells you it has to be a square matrix, it has to be n by n, so it tells you what the dimension of the system is. Okay, so this just to give you a few ideas, once you have the mathematical equations of a physical phenomena, how you translate it in this linear time invariant way. It's of course, these are examples, so there's much more going on behind it, but we'll get to it. So all this is cool and dandy, but as we said before, it really is not representative of many things that are happening out there. Most of the systems that are in place are nonlinear. But we can write nonlinear systems in a much more general way. In a general way, infinite dimensional, time invariant, causal nonlinear systems can be written like this, which is similar to the x dot equals ax plus bu that we saw before. But given that this time the systems are nonlinear, we cannot really write them so cleanly as before, and therefore we have to describe in a general way that we call f and g, the functions f and the functions g, the mapping between the input and the state variables and the x dot and the y respectively. So remember, linear means a very particular thing. Nonlinear means everything else, okay? So it's easy to write specifically a linear time invariant system with these specific relationships. Matrix multiplies vector plus matrix multiplies vector. A nonlinear is a very generic thing. We cannot write it in a specific, it could be a sign, it could be whatever kind of mathematical relationship. So the only way to write it in a general way is just saying, okay, it's an f of the x and the u. It's a g of the x and the u. Some nonlinear relationship. But still, it's better than not writing anything, right? So the question now becomes, in the real world, we have all nonlinear systems. We have all of these things here, of these f of xu's and y is equal to g of xu's. How do we go from this nonlinear representation to the linear time invariant representation x dot equals ax plus bu, y equals cx plus du? And when does it make sense to do so, right? When is it actually a reasonable approximation? So let's look now at a pendulum. A pendulum is a nonlinear system. It's easy, but it's not straightforward. So, okay, what's going on here? We have this pendulum, it's a mass. Let's consider this mass to be a point form a mass. So no actual physical geometry. It's connected to the ceiling through this thing of dimension L. Let's suppose we have, of course, friction that is playing a role, and we've got the input to the system is a torque, okay? It's a torque U that it's an input to the system, so we call it U. Let's imagine it's a torque that we just can apply, maybe because this thing here is a little motor that we can use to turn things around. Imagine it as you wish. So how do we write the dynamical equations? So note that we are talking about how to represent physical systems, mathematical representations of physical systems in some specific way that is useful to us. We're not really treating how do you derive these equations, right? This is something that you should have seen in other courses, in your physics 1, 2, whatever. But the general idea here is that we are looking for an equilibrium of torques. So we're saying, look, if you do the sum of all the external torques that apply on the system, this is going to be equal to j theta double dot, where theta is the angular position from the center. And well, what are so let's take a piece at a time and understand what's going on. Well, the external torques, what are they? Well, we define the theta to be positive in this direction, right? So the sum, okay, maybe sigma in this case, I mean a summatory, okay? I don't mean sigma as the system before. Let's say ti that goes from 1 to whatever they are. And maybe it's a bad choice, 1 to, okay. What are the inputs? Well, we've got the actual input to the system, that is an external arbitrary torque that I can put in, just defined like this. Then we said that we have some friction. Friction is going to be represented as an external torque that opposes the motion, right? So it's going to be, has the opposite sign of the input. It's going to be proportional, so with some constancy times the angular speed. So the faster we go, the more friction is going to be an issue. And then there's going to be something else, of course, that drives the whole deal here, which is the weight of this ball, right? So the weight of this mass is, of course, mg if we are on planet Earth. So this means that this torque here is going to this weight is going to cause a torque that is equal to mg times the distance between where the force is applied and the center of the pole here. So since this is theta and this is a right angle, we can show that this segment here is just for the theorem, I don't remember which one, of rectangular triangles, is L, which is this thing here, times sine of theta. So the other torque, which is always in direction that is opposed to what we call the positive, is mg times the distance L sine of theta. And these are the torques, the external torques that apply on the system. What about J? Well, J is the inertia. It's the opposition to a change in angular position of this mass that we just imagine all concentrated on a point, and it's the center of mass. So J is nothing but the ml squared, which is the distance between, it's Huygens theorem of the transport of inertia. I don't know if you remember this, but if not, just take it for granted. J is basically the mass times the distance squared from the place where you're going to calculate the inertia. So this allows us finally to write the equation like this. ml squared theta double dot is equal to minus c theta dot minus mgl sine of theta plus u. Okay, so this is a little bit more interesting than before, right? How do we translate into a next? Why is it more interesting than before? Because have you noticed before we had either x dot equals to directly the input, or x dot equals to something times x times the input. Now we have something double dot. Okay, so what's going on? We have this, if we would like to label it mathematically, it would be a second order ordinary differential equation, right? We will generalize this result later on, but the cool thing about this state space representation is that it's a systematic approach that allows us to translate always an nth order ordinary differential equation into a system of n first order ordinary differential equations, which is x dot equals ax plus bu. So what's the bottom line? If you're representing a physical phenomena that is described by an nth order ordinary differential equation, well, it's a state space representation. Will have dimension n, which is the maximum level of derivatives you find in the original thing. So how do we get to this? Now, this is very fun, and I would like to do it with a little bit more space. Let's see if I can fit it here. So we want to keep, so we're deciding what the state variables are, right? Again, the state variables, there's this idea of the memory of the system. So what are the physical things here, quantities that give us an idea of what is the history of the past input? Well, definitely it's a pendulum. It's going back and forth, right? So it would be helpful to know where it is. So we call the first state variable x1. We say it's theta, okay? And then you can think about it in a physical way, but I encourage you not to in this specific case. And let's think about it only in a mathematical way. Say, okay, we've got x1 with this theta. It must have something to do with the system, right? It's a pendulum going back and forth. I think it's rather a good guess to say that one of the state variables is going to be the position of the pendulum. But then let's say, okay, x1 is theta, perfect. What happens if I do x1 dot? If I take a derivative, well, if I do a derivative on the left-hand side of the equation, x1 dot is equal to theta dot. Of course, these are all functions of time, right? I'm not writing it out, but these are all functions of time. Well, now let's call this x2. Why? Just because. Okay, we'll define it. Relabel x1 dot as x2. Okay, then what happens with x2 when I take the derivative of it? What's x2 dot? Well, x2 dot is equal to what? It's equal to x1 double dot, which is theta double dot, right? When do I know I need to stop? Because I could do this thing n times. I could go on and say, okay, now let's define this as x3, and then let's do x3 dot, and then x4 dot, and I can go on as much as you want, right? When do I stop? Well, I stop when you've got enough derivatives as the higher order derivative you find in your original equations. So theta double dot was what we had and what we'll stop at. So now, how do we rewrite things? Well, let's look at the equation here. This now became ml squared. Theta double dot is just a complicated way of saying x2 dot at this point is equal to minus c theta dot, which we said is x1 dot, or x2, and minus mgl sine of theta. Theta, we said it's x1 plus u. Now we're getting closer to the equations we had before, but we need another piece of information. How are x1 and x2 related to each other? Well, like this, right? x1 dot is equal to x2. Any questions on this? Comments, doubts? Okay, I encourage you, yes. I need to throw you the boxes so other people can hear you. Here you go.
What will be the output of the system?
Well, what do you want the output of the system to be? It's a design variable. Now, when control systems, you can decide what you want to control. Let's suppose that in this case, we want to control the position of the pendulum, so it's going to be theta. It could be the speed, then it's going to be theta dot. The angular speed. It could be any combination of these.
So at the moment, we don't define any output.
Yeah, at the moment we don't, but look at this. Y equals theta. Now we've got one. It's really like this, right? You can, y in the state space representation, x dot equals x plus bu. Y is equal to cx. C is a vector, x is a vector. What does it mean? It's a linear. In order for it to be a linear system, C can be any linear combination of the states. If you decided that the states, you found out that the states are, for in this specific case, position and angular position and velocity, then your output can be any linear combination of your position and the velocity. Any alpha theta plus beta theta dot. Typically it's either or, but it could be really any arbitrary. Okay, we have 6 minutes to go, and it's going to be 6 intense minutes, so keep focused. Not joking. Because there's something important, we're going to look at it next class just to make sure. So how do we write this out? How do we find ABC? Now we have to be a little bit careful, right? So, guys, still 5-6 minutes to go. So let's now relabel x as the x of x dot equals x plus bu as the vector of x1 and x2. Okay? Now x dot, therefore, is equal to x1 dot and x2 dot, right? So how do we write this? Well, at this point, we want to find the f and g equations. We know this is a nonlinear system, so there's not really... I still need to figure this one out. Okay, whatever. We'll have to do this next time. Thank you for your time.